Welcome to a session on Einstein coefficients and relation among them. To understand the concept of Einstein coefficients, we have to understand the three basic processes in lasers. Those are stimulated absorption, spontaneous emission, and stimulated emission of radiation. First, let us have an idea about what is absorption or stimulated absorption. Let us consider any two active energy levels in an atomic system. For example, here I have taken two energy levels in the atomic energy system. So, E1 is the lower energy level or ground state and E2 is the higher energy level. Mostly the atoms are in their ground state. The question is how to excite them to the higher energy level E2. So, if you supply some energy to these atoms which are in their ground state, obviously they will be excited to their higher energy level E2. But this process can done by several ways. The one of the ways, if you supply a photon, light energy, a particle aspect of the light is called as a photon. If you supply the photon whose energy E equals to the energy difference between the upper energy level and the lower energy level, that which is equals to h nu. So this energy depends upon the frequency of the light. So by taking this amount of energy, this particular atom got additional energy. So this atom will rise from E1 state to E2 state. This process is called as absorption or stimulated absorption. The question is, this atom, how much it will stay in the higher energy level E2. So this is E2 energy level, E1 energy level. Already this atom is there in the E2 energy level by the process of absorption. Here I want to introduce a concept of lifetime. What is the lifetime? This particular atom will stay in this higher energy level for very small time. What is that amount of time? Typically this is 10 to the power of minus 8 seconds for hydrogen atom. It will stay in higher energy level just for that much time, 10 to the power of not plus minus 8 seconds, very much small. After that the atom itself de-excites to ground state, but as it is coming from higher energy level to lower energy level, it has to lose the energy, but it loses the energy in the form of what? A photon or radiation. Okay, this process is called as a spontaneous emission of radiation. For example, here let us consider 4 atoms which are de-excited to ground state, but the problem in this process is all the photons which are emitted in this process don't have same directionality. If they don't have same direction, they don't maintain same phase. Obviously there is no coherence if there is no phase. This is the problem with the spontaneously emitted photons. Now laser requires a special kind of radiation. That process is called as stimulated emission of radiation. So these are the two energy levels, E1 and E2. Here the atom is in its excited state by the process of absorption as like this. The question is how to get stimulated emission of radiation. So the key point here is lifetime. After the lifetime, the atom itself de-excited to the lower energy level and it loses the energy in the form of a photon. So that process is called as spontaneous emission. So which means that we have to do something before its lifetime. So before its lifetime, if you stimulate this atom in the higher energy level with the help of a photon, now this atom de-excited to the ground state. In this process it loses the energy in the form of photon. Here the specialty is this emitted photon is very much similar to what photon? Incident photon. Now two photons with the same direction, with same phase and same wavelength, which are traveling in same direction, are produced. These photons are called as coherent photons, and this phenomenon is called as a stimulated emission of radiation. This kind of radiation is required for the creation of the laser light. So these are the three processes simultaneously happening inside which system? Atomic system. Now let us have few considerations to derive the Einstein coefficients. So one of the important assumption is this. Let us consider two energy levels. One is E1 energy level, another one is E2 energy level. E1 energy level consists of N1 number of atoms per unit volume. So the number of atoms per unit volume in E1 energy level is N1. And let us consider N2 number of atoms in higher energy level E2 per unit volume. So the question is, already you are aware that in order to send these atoms from lower energy level to higher energy level, you need to supply what? Photons. Let n be the small n be the number of photons incidenting on E1 energy level per unit volume with an amount of energy h nu. So here what is n? Number of photons falling on unit volume, and what is h nu? It's energy. So now equal to h nu. So now this is the count, this is what? Energy. I am combining these two parameters. What is these two? Count as well as what? Energy. Then we would get a particular term called as rho of nu, energy density of the incidenting photons. Energy density of the incidenting photons, rho of nu, can be written as n h nu. I already told you that h nu is the energy and n is the number of photons which are falling on the unit volume. So n h nu is the energy density of the incident photons, which will use the number as well as what? Energy with that particular number of photons have associated with. Right. So these three processes are simultaneous: absorption, spontaneous emission, and stimulated emission are continuous process in a atomic system. Now let us try to calculate this upward transition rate. Like upward, there are two types of transitions. So some atoms are going from lower energy level to higher energy level, which represents upward transitions, and some atoms are coming from higher energy to lower energy. So down arrow indicates downward transitions, and this up arrow indicates upward transitions. So upward, first let us try to calculate upward transition rate. So this upward transition rate, so out of three processes which have the upward transitions, only stimulated absorption. Now stimulated, ST means stimulated absorption rate. So this depends upon what factors. So it's directly proportional to, first thing is number of atoms in the ground state. So for example, here the stimulated absorption rate is 1. I supplied one photon, one atom absorbs that photon and excited to the higher energy level. So stimulated absorption rate is 1. Suppose if I supply 2 photons, then stimulated absorption rate is 2. If I supply another photon, then another atom will excite it to higher energy level, and the stimulated absorption rate is now 3. So stimulated absorption rate directly proportional to the number of atoms in the ground state N1, and this also directly proportional to the energy density. If I don't have the number of photons, 3 photons, then 3 types of absorption process, 3 absorption rate is not possible. So it directly proportional to rho of nu. If I remove the proportionality constant, I would get N1 into rho of nu. So if I remove the proportionality constant, I should place a constant. If I remove the proportionality, I should place a constant. That constant is, for stimulated I am opting B, and this is what 1,2, where B12 is called as Einstein coefficient of stimulated absorption. So it is very clear that stimulated absorption rate I obtained as, so stimulated absorption rate, which is a upward transition, obtained as N1 rho of nu into B12. Here B12 is called as Einstein coefficient. This is called as Einstein coefficient of stimulated absorption. Okay, next we will try to calculate downward transition rate. Of course, this is what upward transition rate. Now we will try to calculate downward transition rate. So first of all, how many types of downward transitions are there? Two types. One is by spontaneous emission. Atoms are coming down from higher energy to lower energy by spontaneous emission. Atoms are also coming from higher energy level to lower energy by stimulated emission. So downward transition are two types. The first type is spontaneous emission. And now we will try to find out the spontaneous emission rate. So now the spontaneous emission rate depends upon what factors. So what is spontaneous emission? The atom itself de-excited to the ground state after lifetime and emit a photon. Energy loss will be emitted as a photon. This process is called as spontaneous emission rate. So if one atom comes down, then one photon released. Two atoms come down, two photons. Three photons. If four atoms come down, then 4 is the spontaneous emission rate. So it's quite clear, spontaneous emission rate directly proportional to the how many number of atoms are there in the excited state, E2. So it doesn't require any photon. So after lifetime, the atoms come down to the ground state by themselves. So if you remove the proportionality, you would get a constant. Since it is spontaneous, I would opt a term called as what? A21. Here A21. 21 means from E2 state to E1. So here A indicates spontaneous emission. So A21 is called as Einstein coefficient. What is this? Einstein coefficient of spontaneous emission. So the second kind of downward transition is stimulated emission of radiation. So this stimulated emission of radiation depends upon what factors? You already aware that in order to happen the stimulated emission, I need to supply external photon to stimulate the atom before its lifetime. So it depends upon rho of nu. So if you supply 10 photons, then obviously 10 atoms de-excite to ground state. And one more thing is, suppose if another atom is there, then if you supply another photon, then 2 more photons got released. So the stimulated emission rate increases from 2 to 4. So it also depends upon what? Number of atoms in higher energy level N2, and it depends upon what? Number of photons we supplied with an energy h nu, which is called as rho of nu. If you combine these two terms, so N2, if you combine these two terms and eliminate proportionality constant, you would get a constant. What is that constant? B. Since it is stimulated emission, B 2-1. 2-1 means energy, the transition is making from 2 to 1. So these are the upward transition rate and the downward transition rates. The question is, you are already aware that this is the upward transition. Upward transition, atom going from E1 to where? E2. Let us assume that 50 atoms went up. E1 to what state? 50 atoms went up from E1 to E2. By the process, whatever it is, how many atoms has to fall down to E1 state? Obviously 50. If you throw the 50 balls up, then obviously 50 balls has to fall down. So upward transition rate is equal to downward transition rate. This condition is called as equilibrium condition. Net upward transition rate equal to net downward transition rate. So what is the net upward transition rate? Stimulated absorption rate equal to the stimulated emission rate plus spontaneous emission rate. These are the two downward transitions, and upward transition is only absorption. Let us make A's and B's separate. So here N2 A21 equals to, this is as it is. So bring this value to opposite side. So N1 rho of nu into B12 minus N2 rho of nu into B21. So here N2 A21 equal to, if you take out rho of nu as common, so you would get N1 B12 minus N2 B21. If you want to calculate the value of rho of nu, you would get N2 A21 divided by N1 B12 minus N2 B21. Do one thing. So let us assume that this is equation 1. Let us divide N2 B21 on with the numerator and denominator for making simplification. So rho of nu equal to N2 A21 divided by N2 B21 whole divided by N1 B12 divided by N2 B21 minus N2 B21 divided by N2 B21. So it cancels out. Of course, N2 cancels out. So the remaining term is rho of nu equal to A21 by B21 whole divided by N1 by N2 into B12 by B21 minus 1. This is the leftover term. Let us assume that this is equation number 2. Here I don't know the value of N1 by N2. So how to find the value of N1 by N2? For this, let us have an idea about Boltzmann distribution law. Boltzmann distribution law says that N0 is equal to Gi into N0 into e power minus Ei divided by kT. So this is called as Boltzmann distribution law. What does it say? That it means that, for example, in the E1 energy level, if I want to find out how many number of atoms are there, then put this is Ni is equal to Gi into N0 into e power minus Ei by kT. Take I is equal to 1. So in the N1, in E1 state, how many number of atoms are there? N1 number of atoms are there. That we assumed starting. Okay, but what is the value of N1? Is that 50 or 60 or 500 or 600? So that you can calculate by using this formula. G1, put I equal to 1, where Gi is called as a degeneracy of the ith energy level. So the number of energy levels with the same energy is called as what? Degeneracy. So G1 into N0. N0 is called as what? Ground state atoms. How many number of atoms are there in a ground state? Into e power minus E1. Put I equal to 1 in E1 energy level. How many number of atoms are there? Okay, N0 is the number of atoms in the E0 state, ground state. Whole divided by K, Boltzmann constant into temperature at which we are doing the calculations. So N1. So similarly, put I equal to 2. Put I equal to 2. Then it will use the number of atoms in N2 E2 energy level. In E2 energy level, the number of atoms per unit volume we assumed as what? N2. So this N2 can be written as G2 into N0, number of atoms in the ground state, into e power minus E2 divided by kT. So here what we want? N1 by N2. So let us assume that this is 3. Let us assume that this is equation 4. Make 3 divided by 4. So N1 by N2 is equal to this value. So N1 divided by N2 is equal to G1 by G2 into N0 cancels out. So e power, if you brought this value to the numerator, then this minus becomes what? Plus. So it becomes E2 minus E1 divided by kT. So you can add the powers if the bases are same. According to that rule, we added plus E2 to minus E1 divided by kT. Okay. So since both are e powers, right? We are already aware that E2 minus E1, the energy of the photon, E2 minus E1 equal to what? H nu. So I am avoiding one step by substituting E2 minus E1 equal to H2, H nu. So we got the value of N1 by N2. So let it be equation number 5. Let us put this value, equation 5, in where? Equation number 2, exactly here. Now let us have what happens. So now let us see what happens. So rho of mu equals to A21 by B21 whole divided by N1 by N2 value equal to G1 by G2 into e power h nu by kT. This is the value of N1 by N2. Apart from that, what is there? B12 by B21 minus 1 is there. So let us assume that this is equation number 6. So according to black body radiation, according to BBR, black body radiation, the energy density of photons from Planck's law we can calculate as 8 pi h nu cube by c cube into 1 by e power h nu by kT minus 1. So in Planck's law, which is explaining for black body radiation, which goes with the black body radiation, there we will get the same rho of nu. So by taking that rho of nu into the consideration, we have two rho of nu's now. So let us compare this 6 with the 7, since both are representing what? Rho of nu, energy density of the incident photons. Okay, so now let us make a comparison between the numerators. So by comparing the numerators, what we would get? A21 by B21 equal to 8 pi h nu cube by c cube. This is equation number 8. This is called as one of the Einstein relation between A21 and B21. So obviously what is A21? Spontaneous emission of radiation, emission rate. And this one is called as B21 is called as Einstein coefficient of stimulated emission of radiation. So this is the relation between them. To be frank, we can say A21 by B21 is directly proportional to what? Nu cube. As the frequency of the radiation increases, A21 increases much more, which means A21, which spontaneous emission is more predominant at higher and higher values of frequencies. So for ultraviolet rays, X-rays, we would get mostly spontaneous emission. So this is the more predominant. This is the one of the conclusion of what? Einstein coefficients. And what is the another conclusion? What is the another conclusion? The another conclusion is by comparing the denominators. This is the denominator of this equation. This is the denominator of this equation. So G1 by G2 into B12 by B21 into e power h nu by kT minus 1 equal to this value, e power h nu by kT minus 1. If this minus 1 brought to opposite side, it become what? Plus 1. So minus 1 plus 1 cancels out. So we can remove that. If you brought this value to opposite side, this become what? E power h nu by Okay, if you brought this value to opposite, so same values cancels out, so this value equal to 1. So it says that G1 by G2 equal to B21 by B12 if you brought this value to opposite side, or you can make a conclusion G1 B12 G1 B12 is equal to G2 B21. So this is also the relation between Einstein coefficients. You know what is B21? Stimulated emission of radiation. What is B12? Stimulated absorption. The relation between these two is linked with the degeneracy of the energy levels. So it is linked with the degeneracy. So it indicates that higher the degeneracy, if the degeneracy value becomes very high, the transition rate between these two states becomes also very high. These are the conclusions from Einstein coefficients. Thank you.